Hello everyone, welcome to today's Bangalore Theory seminar. We're extremely delighted to have Professor Santosh Vempala here today. Santosh graduated from CMU in '97 under the supervision of Adam Blunt. He was an associate professor at MIT before he moved to Georgia Tech, where he's currently the Frederick Story Chair and a distinguished professor in computer science. His research interests broadly span algorithms, geometry, randomness, in particular, algorithmic tools for sampling, learning, optimization, and data analysis, high-dimensional geometry, randomized linear algebra. More recently, he has also been studying theoretical models of computation by the brain. Santosh has received numerous awards for his joint work with Richard Peng, an assistant professor at Georgia Tech. Santosh has received the Best Paper Award at SOLA 2021 for their breakthrough work on solving sparse linear systems faster than matrix multiplication. He's also the recipient of a Miller Fellowship, a Guggenheim Fellowship, and a Swan Fellowship. He was named Fellow of ACM for contributions to algorithms for convex sets and probability distributions in 2015. And very recently, in 2022, he was named a Fellow of American Mathematical Society for contributions to randomized algorithms, high-dimensional geometry, numerical linear algebra. He was also the founding director of Algorithms and Randomness Center at Georgia Tech, and throughout his illustrious career, Santosh has advised a cohort of brilliant researchers in theory computer science, two of whom I'm fortunate to be working with. Santosh, thanks for accepting our invitation and stay with us.
Thank you. Just to be clear, I invited myself. Thank you for having me. Yeah. So today's talk is about a classical topic. It's been around for more than 100 years in statistics. Please, so the audience is small enough, you ask me all kinds of questions, and I have a board also. So you can, the talk itself is designed to be sort of an overview of many of the techniques in this area and the results, current status. But I'm happy to tell you whatever I know about related things. So okay, this is the main result is joint work with IISc Bakshi, who's a postdoc right now at MIT, Ilias Diakonikolas, who's a professor at Wisconsin-Madison, Sergio, who's a PhD student at Georgia Tech, graduating this year, Daniel Kane, a professor in San Diego, Pravesh Kothari, a professor at CMU. Okay, so the model is the following. It's a model for high-dimensional data. Right? So we assume the data is coming from this model. It's a probabilistic model. It's a mixture of k Gaussians in d dimensions. So d is the dimension. Each Gaussian has an unknown mean, so some point in space, an unknown covariance matrix, and a mixing weight, wi. The mixing weights add up to 1. So you know that every point is coming from one of the Gaussians. And so basically the way data is generated is you pick a Gaussian with probability wi, and then within that Gaussian you pick a random point according to the mean and covariance of that Gaussian, and you generate points like this. That's this normal model. And so these are the parameters, the number of Gaussians k, which you think of as a constant, and the dimension could of course be very high, and those are the parameters for example. So it was first introduced formally in 1894. I'll mention that on the next slide. So, here is a illustration. The ellipses I've drawn, but the points are actually samples of Gaussians. Of course, there could be overlap depending on because Gaussians have full support. And so the main problem is, given these samples, which you assume are from a Gaussian mixture, try to find the model, find the parameters, or more generally, more precisely, find a Gaussian mixture model which is close to the one that must be generating this data. Because of course you're seeing samples, so there could be multiple answers that are close to each other, and you'd like to find one that's close in total variation distance. So I'll define and stress that this is the natural distance here in this context. But also one could alternately ask after, yes.
It's a naive question.
Yeah.
Is the identifiability sort of here?
Yeah, it's an excellent question. It's asking why is the problem even well defined? Well, when I say it like this, it's well defined because it's just saying, give me any distribution that's close in total variation distance to some data distribution. It don't even need to zoom. But the next line where I say, learn the parameters to within small error. This is not clear. It's a well-defined question because maybe there are multiple possible parameter choices which will result in the same distribution, and therefore it's not uniquely identified. This is not a purely theoretical or abstract notion. It's actually the case. I mean, suppose instead of being in one dimension, let's say your the density of your distribution looks something like this. Okay, it's just on the interval between 0 and 1, but up to here it's up to 1/2. It's some lower density. Up to 1/2 it's higher density, right? And you're seeing samples from this. Can you tell me what but I can think of this as a mixture of intervals, let's say. It could be two intervals, 1 over 0, 1/2, and 1 over 1/2 and 1, right? With different weights. Or it could be 1 over the entire thing and 1 over just 1/2 and 1. And those are completely different parameters, but possible. Now, the nice thing about mixtures, as was established a century ago about Gaussian mixtures, is that no matter what the Gaussians are, there's only one answer. You cannot have two different Gaussian parameters that are distinct and give you the same distribution. Exactly. Of course, error matters. We'll see. So, the first paper is kind of interesting. What he did is he looked at data coming from crabs, measurements of crab physical characteristics, and was able to use this model to conclude that in fact there are multiple species. And later, of course, it was validated. There are in fact distinct species just from this behavioral observation. Yes.
Is there a quick way to see the uniqueness result?
What do you mean quick?
Or what would be the quick way?
There is no elevator proof, but we will see multiple proofs of it as corollaries. The main thing is that you change Gaussian to something a little bit more general. It's simply not true. Right. So what in the case of Gaussians, what happens is that if I take a single Gaussian, of course, it's determined completely by its first and second moments, mean and covariance. If I take a mixture, well, you have a mixture distribution, so it has a mean and covariance. That's not enough. But it turns out if you go to a finite number of moments, in fact, 6 moments are enough to uniquely identify. That's what I was saying.
You can find it.
But k is a constant, so in the worst case we will just iterate. But for the top, let's assume this.
For multiple k, you can have solution. Like give example, for example, you can have 2 or 3 or 4.
Oh yeah. But not for Gaussian. There will be only one. Even if k is a parameter, there's only one solution. You cannot make, for example, one Gaussian look like a mixture of 2 or more. Okay, so this was the case here. Now, of course, he was working with like 50 data points or something like this, and so I do it by hand doing the fitting. But in '98, Sanjay Dasgupta sort of made it a formal theoretical computer science problem and asked the algorithmic question: given these points, can you give an efficient algorithm to actually do it? And the way he posed it is that let's assume that the Gaussians are clusterable, so they are sufficiently separated so that when you look at any point, it's very likely that it's from one of the Gaussians, not from the other. And so under this setting, can you find a cluster? So then the problem is find a cluster. You don't really need to worry too much about identifiability because any set of distributions, if they are sufficiently separated, you should be able to find a partition. Okay, and there's been progress on this in various techniques. There is improvements in the result. There is tight results for clustering, so on. Sort of culminated in this general result by Kalai-Moitra-Valiant, building on and then extended by Moitra and Valiant, which and independently by Belkin-Sinha, which gave a polynomial time algorithm for this problem for any fixed k. So if you think of k as constant, then it's a polynomial time algorithm for solving the problem. Or more precisely, there is a randomized algorithm to learn a mixture of k Gaussians up to delta total variation distance error. So again, I have to define that, but think of it as some error. In time, that's k is constant, right? So this whole thing is a constant, lead to some power times polynomial in the smallest mixing weight. So this is 1 over W min is unavoidable because if the mixing weight is very small, you want to see some points from it. Okay, so, and 1 over delta, the target. So this is the result. So I just wrote it again. What is this TV distance? It's sort of it's asking how much of the distribution needs to be changed to go from one to the other. Like or if you like, it's the supremum over all subsets of the difference in the measure of the distance. Now, of course, that number, that exponent there this is not a practical algorithm. It shows that there might be one. The sample complexity lower bound is 2 to the k. So it doesn't matter what algorithm you use. Just from an information theory perspective, how many samples do you need? It's at least simple exponential in k. But that's all. It's not that. Yeah, and also poly 1 over W and so on. But so on the other hand, if you restrict your algorithm to certain natural models of computation, not general Turing machines, for example, what are called statistical query algorithms, then it turns out that d to the omega k is a lower bound. So not d to the k, but d to the omega k is a lower bound. This is not an information theory lower bound. It's lower bound when you for class of algorithms, which include the ones that we are currently using, but still. So even without going to the main result of this talk, there are some very nice problems here to improve the complexity here. So is there a d to the order k algorithm? Open. And then finding a lower bound that's more general. So for example, this lower bound does not apply to classes of convex relaxations that one might seem natural for this. So now let me introduce the main problem for this talk, which is the robust version of this problem. So these models are great. I mean, they're very clean, nice to analyze mathematically and so on, but they're highly unrealistic because, yes, the model is good, but you expect it to be close to the reality, not exactly the reality. Or at least that's when you want some explanatory power. So some fraction of the data doesn't come from the model. Okay? Even worse, that error could be systematic or malicious or whatever. We don't want to make any assumption on how the error was created. We just want to say there is a model that explains most of the data. Can you find it? So the way we'll model this is very general again, which is that a bounded fraction of the data, say some percent of it, is arbitrarily corrupted. So data is drawn, not by you, but by somebody who looks at it and decides to change 1% of it or 10%. And then you still want to recover the file. Now remember, if you change epsilon fraction of the data, the new distribution is still within total variation distance epsilon of the original. Okay, so you can't expect to do better than epsilon error. But up to epsilon, maybe it's possible. And it is possible in information theoretically because you can try over all possible subsets of changes and then work on that and so on. Of course, that's not efficient. So that's the problem. Learn the underlying model despite its adversarial noise, agnostic learning. So you see, these are all lines I could have put for any generative model. It doesn't have to be mixture of Gaussian. And this is again, this is also originates in statistics. It's called robust statistics in the early 60s. Fisher, Tukey, and Huber, some of the people who talked about this. And in some sense, the very general version says there is some distribution D, but you replace it with an arbitrary distribution D tilde, where epsilon fraction has been changed. And this could be really adaptive. Like they could look at the data that was drawn and then change it and so on. And what we want to do here is there a polynomial time algorithm to robustly learn mixtures of data? So you have data that has been corrupted, you know epsilon fraction, but you don't know which epsilon fraction, and you still learn. Right. Is the problem statement clear? How about one Gaussian? Okay. So not k Gaussian, let's say k is 1. So just one Gaussian. So if without noise, it's a trivial problem. You take the sample mean and the sample covariance, and those are in fact the best estimators, and give you very good rate, just linear in the dimension. But if you have the robust question, it's highly non-trivial. In fact, the core problem within this is to estimate the mean of a distribution robustly, just the mean. Okay, so of course you can apply that to estimate the mean of the Gaussian, but also the covariance itself you can think of as the mean of the distribution over XX transpose or over the quadratic form, right? So basically the mean estimation is the core problem to estimate any moment. And in the case of Gaussians, we just need the first moment and second moment. So that's the core problem. But let's make it even easier. How about you want to do mean estimation in one dimension, but robust, right? So you could say the standard thing to do would be empirical mean and empirical variance. Those don't work. I mean, you're adding arbitrary noise, right? To destroy the mean, you just need to put one point really far away, and your empirical mean is completely destroyed. Okay. On the other hand, probably between some point, the median is a good estimator of the mean, and that one you cannot affect by just moving one point. It'll move only a tiny bit. Right? So imagine you take a Gaussian, and I take 5% of the data, and I move it no matter where I want. If I still take the median, it's going to be pretty close to the original mean. It will be within the 45th to 55th percentile range, and that range is still very close to the mean. In fact, it gives you basically the best possible error in one dimension. Okay, that's 1D, right? So, however, problem becomes hard computationally if you go to D dimensions. What does median mean? First of all, but let's say you're in D dimensions. Mean is clear. The average. What does median mean? So there's some very nice definitions. So yes.
Quick question just to get my base.
Yeah.
I cannot throw away part of the data. Like I can just like subsample maybe 1/3 of the data and assume that epsilon is something small enough, so that I miss most of.
Oh, that would require epsilon to be tiny, right? So let's say I have some number of points, capital N. And the noise we're talking about is 1%.
Okay, so it's not like it's not small.
It's not a vanishing. It's not a 1/n fraction or something like this. Yes.
Okay.
Yeah. We want to be able to handle constant fraction of corruptions. Yeah. But even like 1/log or something like that would be highly non-trivial. Yeah. What you can get away with 1/poly dimension, because then, as you say, simply by subsampling, there's some chance that you miss all the incorrectly labeled. Right. So there is a very nice definition of median in high dimension, which is you take the ellipsoid, the smallest volume ellipsoid that contains, say, half your points, and take its center. You can argue why this is like a median and why it's robust, and why you cannot change it so much by moving a few points and so on. But the minimum volume ellipsoid in general will be you can set up degeneracies, but it will be unique. At least its center will be. Yeah. But the issue, of course, is this is a very hard thing. I mean, it's nice for statisticians. They don't necessarily care about complexity of computation, so it's a beautiful definition. But how are you going to compute the minimum volume ellipsoid in whatever number of dimensions that contains half the points? Nothing about this problem is complex. Or seems tractable. So error guarantee is great for that problem. Actually, if you could do that, you would get good error. But it's all slightly hard, but you don't even have good approximation. So geometric median. This is the idea that let's take the median in every coordinate. You have some basis, take the median in every coordinate. The problem is that you get epsilon error in each coordinate, and that gives you epsilon square root the error overall. There are other ideas. None of them give you both, error guarantee and polynomial. So this is how it happens. Every sort of reasonable estimator seems to be either hard to compute or gives you bad error that grows with the dimension. So in 2016, motivated directly by this problem, in two papers, we found algorithms that show that you can actually estimate the mean, and as a result also the covariance of, in quotes, nice distributions. We'll tell you what I mean by that. It just means that your fourth moments are bounded, in terms of the second. It shouldn't be, cannot do this for arbitrary distributions, but as long as something higher than the second moment is bounded in terms of the second moment, you can do this. And the error is epsilon times square root log 1/epsilon. Okay. Turns out this is actually the best possible information theoretically in this arbitrary corruption model. The type of techniques, the techniques developed here have then been used for a host of problems. You can take basically any estimation problem in machine learning and say what's the robust one. Hidden Markov model. Pick your basically regression, and then you can start doing robust one. And in each case, it was not trivial. It was not just corollaries. You have to develop new techniques to handle various parts. So there is a recent book by Nicholas and Kane that summarizes much of this activity. Okay, so by the way, just to be clear, what this is doing is finding an estimate of the mean. So if your true mean is some mu, you're finding a mu tilde so that this error is small. Okay, how should we say small? It's if you assume the covariance is the identity, then this is small and L to L. You get the epsilon square root log 1. Okay. So in 1D, that would say that this is times the standard deviation. That's the. But more generally, you can write it as if you take this in the norm given by the covariance. That's what it is. All I'm trying to say is it doesn't matter if you apply in a fine transformational space, you still recover. Okay, so now let's go to the problem. What about robustly learning KGMMs? This, indeed, as I mentioned, was the motivation for even the efficient robust statistics questions. And back when Kalai-Moitra-Valiant paper came out, in the communications of the ACM version, I got to write the introduction and already asked the question, can we handle with some noise? It wasn't clear at all to the method to the extent. Even as recently as 2019, it was a completely open problem. Didn't know what the answer would be. It could easily be that the robust estimation problem is hard, even though. Okay, so here's the main theorem. For any fixed k, an arbitrary k GMM can be robustly learned in polynomial time. So remember that there is a randomized algorithm that takes d to the order k times poly subscript k 1 over epsilon. That means that the polynomial dependence here, the exponent can depend on k. Right, just to be clear, poly k means that for any fixed k, it's a polynomial in 1 over epsilon, samples and time, and then it will output a mixture that's within distance, some poly k epsilon. Optimum would be if I make this epsilon, cannot do better than that. Here it's poly k epsilon, so the epsilon to something that depends on it. As a corollary, you can also estimate the parameters in polynomials. Okay. What does this mean, estimating parameters? So it's possible that some components are extremely small, smaller than the noise level. Then, of course, then you have no hope of estimating those. What the guarantee is saying that for every unknown component that's not too small just means smaller than basically the target noise, the noise level. One of the output components will have almost the same mean and almost the same covariance. So you will have, there is a true mixture. There are some tiny components, those we can do nothing about. All of the other ones, whatever you're outputting, that mixture will have a corresponding component with almost as small error in mean and covariance. Okay. This is just a corollary. It turns out that if you can get TD distances, this follows. It takes an algorithm, but this is it doesn't depend on how we found it. So even the approximate one is uniquely identifiable in this sense. Okay, that statement is.
Relevant aspect to note is it's not improper learning, as in you're also giving
A GMM. Yes, exactly. Yeah, and in fact, it will be at most k components. It might be fewer because the original k had some tiny ones, and we make it hold on to more than. Okay, so I want to stress right away that this is a theoretical result. I mean, there is still d to the order k, which may be under control, but there is a poly k 1 over epsilon. Let me tell you what that is, so that I'm not hiding anything. The exponent of 1 over epsilon is k to the 1 over, so it's epsilon to the power of 1 over k to the k squared. So, yeah. For any fixed k, it's a constant, but not. So it's just a complexity result, suggesting that I'm telling you that there is a polynomial time algorithm, but not the one you should be trying to implement. Maybe more the reason why it's interesting beyond establishing this sort of flag or whatever is that it's based on some new techniques, and these seem to be applicable beyond Gaussians. I should mention that in concurrent work by Liu and Moitra, they give some partial results where they can do parameter estimation in time that depends, where the exponent depends on the exponentially on the minimum mixing rate. And also they need the covariances of the components to have lower and upper bounds. But it's a very nice application of generative functions, a different technique. So how do we do? Let's go back to the how the yes.
Does it lead to anything in the noiseless case?
Yeah, you get a completely different algorithm, and you get something if your target error is so basically the k to the k squared exponential dependence is only on the target error epsilon, not on the dimension. So previously the complexity was d to the k squared basically. Now it is d to the k times 1 over epsilon to the k squared. If there is no noise, you can pretend that the noise is whatever is your target error, and then you get that. So unless you want noise, you want error that's smaller than polynomial in dimension, it's better algorithm. And so it is nice that just taking on the robust sort of more general problem not only gave you a different algorithm, but actually turns out to be more efficient in the range. Yeah. And there is no reason that k to the k squared exponent is the right one. It's just what we are able to prove. Okay, so just to get an idea of how some of the challenges we will have to overcome, let's look at the noiseless case again. So the algorithms are all based on moments for the last case, right? So principal component analysis, which is second moments, isotropic transformation, making the covariance the identity, also second moments. In fact, all you need is the first 6 moments and only along random directions. So I will sketch the algorithm of Kalai-Moitra-Valiant in a minute. Yeah, let me do that now. In fact, so how do you do it? Let's say there's no noise and you have a bunch of mixtures. How can we hope to solve this problem? So the way they do it is following. They say I have these Gaussian somewhere in space, right there. Some kind of it's just these samples. Let me pick random direction. We project the Gaussians along the region. So every point x goes to x in a product with some direction. That's this region. So now what happens? Gaussians, projections to Gaussians, projections of Gaussians to Gaussians. So you get something. Okay. Now let's say you could solve the 1D problem. Gaussians are still uniquely identifiable in 1D, many dimensions. So this problem is solvable. Of course, what does solvable mean? You can find the means and the variances. So there's only one variances of each of the projected distributions. Great. So do this many times. Right? So instead of 1B, do this for a whole bunch of different B's. And each of them, so if the true means are mu1 to some mu k, when you estimate the means, each of them gives you an equation. mu1 dot v1, say, is equal to something, a1, and then mu1 dot v2 equal to a2, and so on, right? The mu's are known, the v's are known, you chose them. The a's are, you estimated them. So these are linear equations. You can solve the linear equations, right? And you're done. Well, not quite. Here is the catch. So that's the idea. Problem is this. So suppose I have just 2 Gaussians. In 1D, I estimated these means to be mu1 and mu2, right? Along some. Now I have another projection, and along this I got something, and I got two estimates of the mean. How do I know which of these are matching and which of these are not? Right, this is the mean of the first Gaussian, this is the mean of the second Gaussian. First and second are local. And here, some first and some second, how do I know one is the same one and two is the same two? I don't want to incur this all possible scenario. So what they did is pick a random direction first, and then you're going to pick many random directions that are all close to it. Okay? So each of your directions onto which you project, they will all be quite close to each other, but still random. The randomness is enough to make the linear equations linearly independent. So the solution is still linear. And the fact that they are close means that the ordering is the same. The Gaussians are, you assume, are somewhat separated. So you will make right, these small enough so you don't see a flip in the center. So that's basically the algorithm. Only part I haven't told you is how to do it in 1D. That turned out to be technically the hardest thing in their paper, how to do this in 1D. And in 1D, what they established is that by using the first 6 moments, you can write down equations, and with enough samples, polynomial samples, you can solve it. Okay, so that's one. Now, the trouble, yes.
In the spirit of keeping k constant, couldn't they have looked at all possible? So you have k equalities, right? One for each mean. So you just look at all possible k factorial systems of linear equations. But I guess how do you verify which one?
Yeah, no, one nice good point. You could potentially do an exponential in k search here. There are two complications. At first is that the covariance becomes a much more complicated issue, right? Because the trouble is the number of equations you require here for the mean is already going to be linear, right? Because the number of variables is in the dimension. You have n things here, and then for covariance you really have n squared variables. You need n squared projections, and so that blows up one thing. And we have to try all possible combinations of the n squared projections. All possible permutations of the n squared, which is now becoming exponential. So the number of projections is not so small because the number of variables is high. But say one more thing about that, but maybe that's already said why you can't do that. Yeah. So the problem with trying to make this robust is we know that moments are arbitrarily corrupt, right? Just the mean, for example, is arbitrarily corrupt. But what about if we use robust mean? That's what we did. We can do robust mean. We can do robust moments. The trouble is that because we are going to estimate the means of these projections up to some error, and then use the corresponding solutions to estimate the value in the high dimension, the error that you can tolerate one dimension turns out to be only epsilon or about square root d. You want epsilon in the final answer. This is the best you can hope for, and not really need to do this. But we can't estimate like this. If you have epsilon corruption, you mean really change that. Can change that. So simply taking the components where they estimate the mean in the moments and replacing them by robust versions is not going to work. Okay. So this is the first part, saying that in fact the moment tensors can be estimated robustly. And the way they do this is an extension of this mean estimation work, where basically they set up a convex program, where the convex program tries to pick out the non-noise, some fraction of noise, tries to pick out the non-noise points. And how do we identify non-noise points? Well, the non-noise points are really Gaussians, and Gaussians satisfy certain inequalities. In particular, they have these higher moment inequalities, and that lets you say that this part of it is Gaussian. The noise part, if it looks like Gaussian, great, then it didn't matter anyway. It won't have effect on it. If it doesn't look like Gaussian, it won't satisfy the endpoint. That's the plan. And then they get poly epsilon error of the to estimate the moments. That's not enough to solve this problem because in this mixture they have the issue with how much noise is involved. So, but this is too large to give robust guarantees. Using robust moment estimation is not enough to get robust guarantees for the mixture problem, simply because they blow up by factors of 2. Okay. So, nevertheless, we will use one key idea from this work on robust estimation of moment, which is that in the case when the components are separated, let's say, so going back to the clustering scenario, then it turns out that this convex programming method is quite effective. So if the mixture is clusterable, let's ignore the word partially for a second. Suppose that every pair of components is far apart in total variation distance, which is the natural notion again, right? As two Gaussians, they are separated. Then the clustering itself can be done robust. So if the original components are far enough apart, even though you're adding epsilon noise, you can still cluster. And this was done in 2 parallel papers that gave algorithms for clustering. In the case when the uniform, the mixing weights are uniform, in terms of the data is crucially, yeah, and we assume every pair is far apart. There is a key idea there that we will use, so I will mention it, and then I think it might be of independent interest. If two Gaussians have large TV distance, so that's a probabilistic statement, right? That if I pick points on this distribution, this Gaussian, that Gaussian, the overlap is small. This converts to a very geometric statement. It implies that either the means are separated, sufficiently separated, or the covariances are separated in Frobenius norm, which means that if I take the two covariances, take the difference and take the Frobenius norm, it must be large. Or they are spectrally separated. It means that there is at least one direction in which the variance of one of them is much higher than the variance of the other. So let's look at this geometrically. So if you have two Gaussians that are separated in total variation distance, so the probabilistic overlap is small, one of these cases must happen. If the means are far apart, so then of course the mass of this Gaussian on this side, the mass of this Gaussian on that side is small. Or they are spectrally separated. There is some direction in which one of them is narrow and one of them is wide. So most of the distribution of one guy is here, the other one is outside, so you get small overlap. Or they are Frobenius norm separated. So if you look in any one direction, separation is negligible. But overall, they get this. One of these must happen. That's it. That's just it. If and only if up to constant factors there. Okay. So what we can do using the convex relaxation based clustering algorithm of one of those papers is get an algorithm that does the clustering for the separated part case, but the dependence is exponential in the minimum mixing. So it's d to the power of 1 over minimum mixing. That's not a polynomial algorithm. So what we do is, turns out that the reason you get this dependence is because of that spectral separation condition. There are 3 conditions, right? And 2 of them are easier than the third. The mean separation case and the Frobenius norm separation case are somehow easier to handle than the case where there is one hidden direction in which one is larger than the other. Let's ignore that case. Only worry about the other 2, right? And in the other 2 cases, we can do it much more efficiently. So, robust partial clustering. Partial means as long as, so total means that you assumed everybody is separated. Now let's say it's not the case. Maybe some subsets are separated, some pairs are separated, but not every. So you want to cluster up to the point where now each cluster has different Gaussians, which nobody is separated. We call it out there. That's the goal. Get down to the case where every pair of Gaussians is closing, has some bounded TVs. So this you can do in time that's really polynomial, no k, nothing, times epsilon dependence is 3. But remember, this does not account for if there is one direction in which one component at a time. This is based on a new semi program relaxation to identify a single cluster. And SOS has been a good framework to design algorithms, but in many cases they are replaced now with more efficient, more direct algorithms. This is one case where we don't yet know how to do this. This partial clustering, we still maybe it's possible it hasn't worked as well. If you're looking to understand SOS, this could be an entry point to solve a problem as well.
One thing, so the statement says that under the assumption that the separation is either by mean or by Frobenius norm, you can do it.
Yes. Yes. Otherwise, we are left with the case where either the total variation distance is already, there's an overlap, or they are separated spectrally. So that's where we have landed. Yeah, exactly. Yeah. So I'm just stating this problem. Can you do this without SOS? I think it's a good way to understand the structure. Okay. So now we're down to this thing where you cannot cluster. At least you cannot cluster by mean or by overall Frobenius norm code. The nice thing though is that now you take each of these, let's assume the whole mixture is like that now, because we'll work on each of these separately, and you put it in isotropic position. You assume the mean of the entire mixture is identity, covariance of the entire thing mean is 0, covariance is identity, and you can do that up to epsilon by using moment estimation of the entire distribution. And you can do that now because everything is bounded. If you see if the total derivation distance was high, then you cannot say that the means and covariance are bounded, and you cannot apply a robust estimation. But now you can. That's the advantage of getting to different stuff. So in particular, just to do a little, at least some algebra, if you look at the mean times its transpose or the deviation of the overall covariance of the identity, these are small because we estimated, we made it isotropic. This is close to 0. That's close to sigma is close to identity. And this implies that each component must have bounded mean, simply because the combination of these is close to 0. And each component must have variance close to identity. That's what it means. If the Gaussians are all close and you put the whole mixture in isotropic distribution, each one is close to it. It has bounded distance from identity. I mean, I'm just writing triangle inequalities here. Actually, this should be inequalities. Right? Triangle equality is still but now, okay, fine. Great, but still need an algorithm to identify. Right? They're all close to identity, and the means are all bounded, but you still need to identify them. And for this, we will use moments, but in a different way. The key idea comes from a paper of Belkin, where he did it for 2 Gaussians with equal mixing weights. And rather than just using raw moments, expectation of x squared, x to the 4th, so on, he uses the hybrid polynomials, which are, the polynomial of degree k will be it's a degree k polynomial, but not just a single power. It's a combination. So, for example, the 4th one will be like x to the 4 minus 3x squared plus constant. So that turns out to be much more convenient. And what he said is that if you take the degree 4 Hermite polynomial tensor of the variables, think of the variable as x, take the degree 4 Hermite polynomial applied to the vector x, then that will be a combination, according to the mixing weights, of this tensor. It's a degree 4 on vectors, right? So it's a 4th order tensor. It's an outer product of 4 vectors. The first term is sigma I minus I times sigma I minus I, which is exactly what we want to measure, because each sigma I we know is close to identity. The point is, how is it exactly different from identity? So it's this outer product, plus this times the mean, plus the mean times itself. So this is what it ends up being. So that's the nice formula. And this holds over a sum. So this you can estimate. You can estimate this quantity, but you don't know what the sigma i's are individually. You don't know what the wi's are. You don't know what the mu is. So that's what. Now, if you go back here, this is the main term. You see, this has full rank. So there's a matrix times matrix. This is matrix times 2 vectors. So it's like a low rank 1, not rank 1, but it's a rank 1 matrix times 4 matrix. So this is what, and by symmetry I mean you see, when you do this outer product, there are many ways to combine the indices. You just want to take all the three natural weights and take the average. That's what we mean by sigma. But that's what the Hermite polynomial will actually do. Now here's the key idea. We'll just use random contractions of this. By that I mean, imagine you take that fourth order tensor, multiply it by a random vector twice, two randoms. And it will go from a matrix, from a tensor to a matrix. Because every time you apply by matrix by a vector, it becomes a vector. 3 tensor times a vector becomes a matrix. 4 tensor times a vector is 3 tensor times another vector makes a matrix. So I'm reducing it to matrix by applying two random vectors. What happens? You see, I guess I should look at this one here and apply two random vectors. When I apply two random vectors, if I apply to this term, you'll be left with what you want, sigma minus. When I apply to this term here, right, this part might have survival or it might vanish and you'll be left with a low rank term. And here, this will just become low rank, of course. So you get a rank, constant rank term plus the matrix, plus a matrix. Okay. So now that's going to be the idea. When you apply two random vectors, you're down to the basic matrix that you want plus rank, constant rank term. Now you do this k times and take a random linear combination of those. And that means that the total low rank terms are order k squared now. You've done it k times, and each time you got constant error for each one, so order k squared total rank error. And then there's also error in the estimation itself. So that's the problem we're going to be down to. I give you this matrix, which has error both in low rank terms and also in Frobenius norm. You want to estimate this matrix. We'll be able to do that. So that's the algorithm. We collapse along random vectors, take random linear combinations, and when you do this, the claim is that each of the unknown covariance matrices that you want is going to be close to one of the random contractions with high probability. There's some probability that you're actually hitting one matrix when you do this combination. So basically, to hit the matrix, there is some probability that if you just by chance you pick the right combination, and we'll try this enough times to be exponentially k, but only exponentially. Yeah. And so that just means that since we don't know which one is the right one, we'll get a big list of possible candidates of low rank, low dimensional subspaces. In each of those, we'll solve the GMM problem, and at the end of the day, we'll take the best hypothesis. You can do hypothesis testing. If you give me two different candidate mixtures and there's data, you can use the data to validate which of them is, even noisy data, to validate which of them is actually the better hypothesis. So that's what we'll do. Yeah, okay, so that's the kind of quick view of that part of it. Now, it's important though that after you applied your estimate and you got a covariance matrix, if all the covariances are large, then there's no problem. Then separation in Frobenius norm and spectral norm are the same thing. But if some covariance is small, some variance is small in some direction, some eigenvalue of the covariance matrix is small, then it's possible that the Frobenius norm won't detect it because that was small anyway. So if the true answer is 0, for example, if one of the covariances is lower dimensional, right? The Frobenius norm error, even if you come up with an answer which has some thickness, will be small. But in terms of TV distance error, that's huge. Your Gaussian is concentrated in lower dimensional space, whereas the Gaussian I'm outputting has some variance. No matter what it is, it's a bad answer. So what we'll do is we'll look at the candidates, look at small variance directions, and in those directions, if we'll see if there is separation, and if there is, we cluster and recurse. But now, because we have candidate covariances, we can actually enumerate the possible bad directions and go on. Just a small eigenvalue. Okay, so this is what the overall algorithm looks like. And then we have the corrupted samples. We don't know anything about the mixing weights, right? We have kind of guessed if the minimum weight is at least something. If the minimum weight, smallest weight is too small, smaller than your noise threshold, then we pretend that there's one less component. That's just noise and go back. Then we make the distribution isotropic by robust estimation of the covariance. Now you check if they are mean or Frobenius. This is mean or Frobenius separated. If they are, you do partial clustering and go back on each cluster. If they are no longer mean or Frobenius separated, you do this tensor decomposition, where we estimate the tensor and then enumerate a list of possible candidates for the covariances of each of the components. Then you look at eigenvalues of the covariance matrices. Okay, if one of the eigenvalues is small, you need to spectrally separate them. And then whenever you do the spectral separation, you go back. So you cluster it for that. If the covariances are all large, you've got a potential candidate hypothesis. This is going to be an exponential decay list of hypotheses. And now we do a tournament on those to figure out what is the best one for this. That's the overall. Yeah. It's not meant to be understandable. I have to read the paper every time I project some piece, but yeah. But it is kind of saying that this Gaussian mixture problem has been quite interesting. Even showing without noise in polynomial time took some nice techniques. Now to show that with noise you can do it seems to force us to do new techniques for tensor approximation, clustering, convex relaxation. Yeah. So I would guess, based on this history, that getting this better algorithm for this will be fruitful more generally. Even though this problem in quotes is solved formally only up to polynomial time. So then here are some future directions. Gaussian's great, but why should it be Gaussian? You could have mixtures of other kinds of distributions. What can you hope to solve? This is interesting both with and without noise. I already mentioned, can we do these things without sum of squares, which itself is an efficient way to do things, but also it will reveal some additional structure. And then finally, what about really polynomial n is supposed to be dimension, and I don't even want d to the k. I want d to the d squared. Right? What can we hope to do? And also robust. There are special cases of this situation, but what's the most general setting where you can hope to get a polynomial, including k? One problem here, maybe that's open and nice, is robust or not to learn a polytime. So I give you uniform random samples from an intersection of half spaces, and you want to find an intersection of half spaces that comes within small TV distances. And that's open with and without noise.
Learning, so Gaussian mixtures that can be learned in polytime in n and k. So what special cases are not?
Yeah. So if you know,
I mean d and k.
D and k, yeah. So if you know that that, for example, that every Gaussian can be separated from the rest by a half space, right? So in other words, it's mean separation. So that if you there is a half space, so that most of one Gaussian lies on this side and another has right on that side. And that's true for each of the components. Then there's a polynomial. For example, yeah.
So what about two the sum f of k times poly?
That would be very nice to hear.
Yeah. Do you know any special cases about that?
Beyond what I just described. Well, yeah, I mean, especially if you don't assume clusterability, it's kind of open. There's a result by Shu and Kakade several years ago, where they show that as long as the means, but it's only for spherical Gaussians, so some assumption comes in. Covariances are multiples of identity. As long as the means are linearly independent, so basically the algorithm depends on the smallest eigenvalue of the matrix of the singular value of the matrix of the means. You can do them for one of that. You don't need any further assumption. you need linear independence of the means of the components and spherical Gaussians. There are extensions of that to general Gaussians with suitable assumptions. But there isn't a picture of what is the polynomial in everything.
Like k is 2 or 3.
Yeah, so for k equal to 2, I mean, what we have is a polynomial algorithm. So for any that's the catch. For any constant k, yeah, it's polynomial. I mean, we have an epsilon to the power also. That there's a question of really do epsilon, but otherwise you can do, yeah.
This assumes that the model is a mixture of Gaussians.
Up to epsilon error. Yes.
But what if you do not know that? You have some data.
Yeah.
And you want to fit a mixture of Gaussians to it.
Right. So what you can do here is you can fit the best one, assuming there is one whose error is small, smaller than some constant one. Of course, you could argue that's reasonable. Because let's say the best fit Gaussian gives you total variation distance error 0.2. Maybe that's not the best model for you anyway. But regardless, whatever is your threshold, up to the threshold you can find a mixture as long as the one exists. Yeah, that's the nice thing about the robust part. You don't need to assume that the data is coming from it. Is there one that's within the target area?
Can we relax problem in the sense that it doesn't assume an adversarial corruption?
Yes. So we don't take advantage of that. Absolutely. On the other hand, I mean, if you're saying worst case problem, then it's if you're saying the data is arbitrary and you want to fit the best Gaussian, should be at least as hard because the data could come after corruption or something.
So if you could extend this to log concave densities, would you use it to estimate the volume of non-convex modules, say atomic?
There are two questions there. First question is, can we extend this to general log concave mixtures? That's open. We don't have to do that. Remember, first example I showed you with the intervals. That's already not a log concave mixture. The intervals are log concave. But there one can hope to find a mixture of log concave densities. That's not unique. So forget about parameter. So up to finding something in the PV distance error, good problem. It's open. We don't know the answer. One of the questions here, in fact, the first one there, beyond Gaussian mixtures, turns out that if a certain geometric conjecture called the KLS conjecture is true, then a lot of what we're doing here will extend to general log concave mixtures. That's a conjecture about log concave mixtures. But about your second question of whether estimating them and computing volumes, those are kind of two different problems because it's not clear that. Yeah, well, if you are concave, what is the question in this case? You want to find it's just a density, the integral is 1. So I mean, I don't need to give you a sharp answer, but the problem is not completely well defined. I know what you're trying to get at. Let's say you have a mixture of convex bodies or something, and you want to compute their total volume. If you could estimate the bodies, then you're done anyway, because then you would estimate each one's volume separately. Right? That sense. Maybe there is an interesting direct way to state that.
There are no more questions at this speaker.
T-shirt to wear the next time you come.
Yeah.